Hey everyone, welcome back. So lecture number 10, we will start with electricity today. So in chapter 5, so I think you guys are very familiar with electricity, right? In the winter, these days, it's easy to get electric shock, right? When you are touching the metal doorknob or whatever, or touching somebody, right? So, or like when you slide down a slide when you're a kid, so you might realize your hair sticks up, or a cat that's been playing with this small foals and were able to attract them. Okay, so that's also all the electricity. So we know you can make charged particles by rubbing one material against another, right? So then after you have done that, for example, piece of fur and an amber rod, you rub against each other, so you'll be able to pick up small particles, right? So before that, it's not doing that, but after you rub the rod against the fur, then it will do that because then there's charge on the rod there. So we know that there are two types of charges, positive and negative, and like charges repel each other, opposite charge are attractive to each other, okay? So there are only two types, positive and negative. And this will actually assign randomly. So if you are the guy to discover charges, then you can name them the other way around if you want, okay? So the quantity that we use to, or the symbol we use to describe charge as a quantity is small q, and or in some textbook people might be using capital Q, okay? But the SI unit for charge is Coulomb, C, capital C for that. So the fact that you can rub one material against another to get both material charges is because different materials, their atoms have different tendency of losing electrons, okay? So in that sense, so for example, amber and cross, you can rub them against each other. So then initially, both of them are neutral after you rub them against each other. So it's likely amber going to be negatively charged and the cross will be positively charged. So cross actually loses charge to amber in that sense. So the source of charge is inside an atom, there's nuclei that is positively consists of protons and neutrons, which protons are positively charged and neutrons are neutral. That's why it's called neutrons, why they are called neutrons. And surrounding the nuclei, there's electrons orbiting around. So electrons are negative charged, okay? So if the electron is being separated from the nucleus, then the atom becomes positively charged. Okay. So if another electron, another atom gains electron, then that atom becomes negative in that sense. All right. So again, as I mentioned, it depends on the tendency, like of the materials, which ones are easier to lose electrons and which ones are easier to gain electrons. So for rabbit fur, they have tendency to be positively charged. Glasses, positive charge. So the number of plus signs, that means the tendency, the strength of their tendency to lose electrons. Okay, so on the other end, so these materials have tendency to gain electrons, so they are negatively charged after rubbing against another material from the top there. All right, so if an object is neither positively or negatively charged, then it's called electronically neutral. All right. So at the end of the day, the charge should be conserved. If you are rubbing one thing against another one, so that will be just transfer of electrons from one object to the other. So, but charge overall should be conserved. Okay. So the net charge should remain constant. Another note on charge is quantified. So charge doesn't increase smoothly. So they are actually discrete. They add up by a small portion of called electron charge, which is 1.60 times 10 to the negative 19 coulombs. Okay, so you cannot go further smaller than this number. So it has to be making an increment of either this number or multiples of this number. So for 1 coulomb of the charge, so then there's about 6.25 times 10 to the minus 18 electrons in it. Other quantities. So E, this is a fundamental constant. Okay, so that's one of the constant number. And other constant numbers you might be familiarized with is the mass of electron is 9.11 times 10 to the minus 31 kilograms. So that's a constant number. Proton is also its mass is also a constant number. It's 1.673 times 10 to the minus 27 kilogram. Neutron, mass of neutron is also a constant number, 1.675 times 10 to the minus 27 kilograms. Okay. All right, let's take a look on one simple examples on calculating charges and number of fundamental entities, their electrons and protons. All right. So this problem says you have a system of 1525 particles, each of which is either an electron or a proton, has a net charge of minus 5.456 times 10 to the minus 17 coulombs. How many electrons are in the system? And what's the mass of the system? Okay, so electron has a charge of 1.6 times 10 to the minus 19. So we can write that down for electrons, E, and that should be negative, okay? 1.6 times 10 to the minus 19 coulombs. For proton, it'll be the same, but it will be positive. Okay. So Q, well, let's do this. Q for electron is minus 1.6 times 10 to the minus 19 C. Q for proton is positive 1.6 times 10 to the minus 19 Q. And let's call the number of electrons as M sub E. So you're looking for that. And then you are looking for also the mass of the total of the system, so A and B. All right. So it says total particle, right? 1525. So you can write that number of electrons plus number of proton. That's 1525 of them. It tells us the total charge, net charge, right? So net charge should be equal to NE QE, right? Plus NP QP, right? So that equals to minus 5.456 times 10 to the minus 17 Coulomb. And QE and QP, one is negative, one is positive, are 1.6 times 10 to the minus 19. So then these two equations becomes NE plus NP equal to 1525, NE minus 1.6 10 to the minus 19 C plus NP 1.6 times 10 to the minus 19 C, right? That equals to minus 5.456 times 10 to the minus 17 C, okay? So two equations, two unknowns, right? So you guys can figure this out. Shouldn't be too hard. So at the end, this will be for NE, it's gonna to be 933, okay? And you can also calculate NP. So this is for part A. Part B, NP, or not part B, but you need NP, number of protons for the second part. So 592, okay? So for part B, then you are looking for the total mass of the systems. So you again need to use the two constant numbers for the masses of the electrons and protons. So they are, again, the fundamental numbers, okay? So mass of electron, mass of the electron, yes, is 9.11 times 10 to the minus 31 kilogram. Mass of proton, that is 1.673 times 10 to the minus 27 kilogram. So then the total mass of total should be equal to number of electrons, mass of electrons, plus number of protons, mass of the proton, right? So 933 times 9.11, 10 to the minus 31 kilogram, okay, plus number of protons, 592 times 1.673, 10 to the minus 27 kilogram, okay? All right. So it turns out to be 9.91 times 10 to the minus 25 kilograms for the total mass, okay? You can see that the mass is largely comes from the protons, because protons are much heavier than electrons. Okay, so let's go back to the slide. All right. So the fact that charged particles can pick up small objects. So for example, if you comb your hair with a comb, now of course your hair has to be dry. And then you can approach your comb close to, if you make a small stream of water out of the faucet, you actually make this guy curved towards the comb, or pick up small like pieces of papers. Okay, so that's because when this comb is charged, so let's say it's positively charged, when it's approaching the small particles or here or there, so the molecules inside the particles or inside the papers or the water here actually will reorientate. So then or maybe for atoms, not just molecules, but so they will reorientate. So because for whatever the atom or molecules, you'll find there's nucleus and which is positively charged, and the electrons are negative charge. So you can reorient. So then the minus charges will be closer to this side, and then the positive will be on the other side. So you will rearrange. So that's why. So then positive and negative attract each other. Okay, so in that sense. All right. Move on to the next section on conductors, insulator, and charging by induction. So for materials, you can characterize them into two types. One is called conductor, and the other one is called insulator. So conductor, it will conduct electricity, so simply. So for conductors, those are the materials whose conduction electrons are free to move throughout. So the conduction electron typically will be the most outer shell electrons inside the atom. Okay, so in chemistry, you learn that atoms have the electrons are orbiting the nucleus in different orbitals, right? Some are closer to the nucleus, some are further away. So different layers, or we call different shells in that sense. And an insulator then is the other way around. So insulator whose electrons then they are seldomly moved from atom to atom. So that means they are actually attached to the or bounded to the nucleus strongly. So they are not easy to hop from one atom to another. Okay. Most metals are conductors, and non-metals are mostly insulators. You can charge particles by contact. So that means you have a charge rod here that you move this guy close to a metal piece over here and then in contact. Okay. So before it's touching the metal here, actually it polarized the metal material. So more negative charges will be on this side closer to the rod, and then positive will be expelled further away. So then when they are in touch, the negative and positive will neutralize each other. All right. And then after that, you remove this guy. So then we'll totally, because there's negative charge being moved to the rod. So then overall, you have positive charges overall. So then this guy now will be charged positively in that sense. Or you can do charging by induction. That means the charge rod you are approaching the sphere here actually is not touching that. But in this case, you have two metal spheres in contact initially. They are neutral. Now you have this charge rod approaching that. So then you will polarize this two spheres as one system. So on this side, it'll be more negatively charged. So basically, the electrons going towards that side, right? And then the other side, leaving the positive charges on the other side. Then once you do that, you have charges created on the two sides. Now you separate those two, keeping this still in the close vicinity here. So then these two now are charged. Now you can remove this guy. So then now you have negative charge here and positive charge here. They cannot cross each other, so they will not neutralize. So both spheres will be charged. So this is charged by induction, which means you are not having a charged particle that is touching the metals here, okay? And again, by induction, there's another way of doing this, not just using two metals, but you are using one metal with a conducting wire that is grounded, okay? So when it's grounded, so initially this is not grounded. When this guy's approaching, this charge rod is approaching here, so positive on this side, negative on this side will be there. And at this point, you can ground it, this whole sphere. So the positive charge then will move to the ground because it's repulsive to the positive charges on the rod, okay? And after that, you will cut this off. So then this will be negatively charged, all right? Now you can move this away, so then this metal will be negative charged, okay? So by using two metals in contact initially or one metal with ground line, you can also do charge by induction. All right. Now, earlier we mentioned about the interaction between charges, right? Like charge repel each other, opposite charge attract each other. So for negative and negative, they will repel each other. For negative and positive, they will attract each other. So for repulsive force, you can see they pointing away from each other. For attractive force, you can see they pointing towards each other. Okay. So for any two charges in space, the interaction between them, the forces on each of them is actually a pair of Newton's third law, action and reaction forces, okay? They will share the same magnitude but opposite in direction, and then it's acting on different objects, okay? So on this case, for the like charges, for the opposite charges, you have the two forces, same magnitude but pointing towards each other, okay, in that sense. So the magnitude of this reaction force is proportional to the charges Q1 and Q2 and inversely proportional to their separations, okay? So if they're farther away, the charge will become weaker. So the equation to write is the force equal to a constant number times Q1, Q2 over R12 square, right? Then that constant number happens to be 1 over 4 pi epsilon naught, where epsilon naught is a constant called dielectric constant of vacuum, which is 8.85 times 10 to the minus 12 Coulomb square over Newton times meter square. Or you can just say this Coulomb's constant Ke, which is 1 over 4 pi epsilon. Okay, so that's 8.99 times 10 to the 9 Newton's meters square over Coulomb square. Or some people just say 9 times 10 to the 9. Okay, so that's also about the same because 8.99 is about 9. So these, again, forces are action and reaction forces, okay? So for like charges, positive and positive, okay? So that's the scenario here. Positive and negative will be here, this case, and then negative and negative charge will be in the case of C, okay? So the repulsive forces then. If you have more than two forces in space, then the force, there will be force on a particular charge by all other forces. So for example, on Q1, it will experience forces from Q2, Q3, Q4. Okay, so from Q2 on Q1 will be pointing in this line, in this direction, the direction that connect Q1 and Q2. And between Q1 and Q3 will be this force, okay? And between Q1 and Q4 will be this force, okay? So in that sense. So on Q1, there's three forces acting on it. So then the total force for Q1, that should be the vector addition of force by 2, by the second charge, by the third charge, by the fourth charge, okay? So you add them up in the vector addition, okay, format. So follow the rules for vector additions, okay? Vector addition graphically way, you just put the second vector's tail on head up first, and then the third one on the tail on the head the third one's tail on the head of the second one. Okay, so the resultant will be from the tail of the first one pointing to the third one, the head of the third one. So this is the resultant on F1 on the first charge called F1. So let's take a look on here, one example. So this one says you have three charges are at the vertices of an equilateral triangle as shown in this figure. Down here, the charges have the same magnitude Q for each of them. So they are all Q, but different signs as indicated in the figure. So 1 is positive, 2 is negative, and 3 is positive. Rank the 3 charges in order of increasing magnitude of the electric force they experience. Indicate tides where appropriate. B. Given the redirection angle of the net electric force experienced by charge 1, and then C. Repeat part B for charge 2, D. Repeat part B for charge 3. Okay, it tells you X is horizontally to the right, vertically to upward is the y direction, and that's a directional angle. Okay, Q1, Q2, and Q3. All right, so the electric force between any two of these, right? They should have the same magnitude because it will be K Q of 1 and then Q of 2, right? Over R squared. R will be the side of equilateral triangle, which are the same on the 3 sides. Okay, so let's take a look on here. So let me quickly sketch the equilateral triangle. That's number 1. This guy says it's number 3. And with this one being number 2 down here. So this guy's negative Q. This is positive Q, and this is positive Q. So force on 1 then will be, so this is positive. Okay, this guy's negative. So force on 1 by 2, that should be attractive, right? So it should be this one here. So let's call this force of 2 on 1, okay, in this direction. Force of 3 on 1, then will be in this direction. Okay, the same magnitude, so we'll draw about the same length for this force compared to this guy. So these two add up, right? Then we should be going in this direction. Okay, so this is F of 1 total. You can move this guy over, right? So it will be that. So for equilateral triangle, you can see from the geometry, right? So these two are the same with each other. So then for the angles here, okay, so let's do this. This guy would be 60 degrees, and this will be 60 degree, okay? And this one will be 120. And then this force over here should be dividing this angle into 2 equal halves. So these two should be also 60. Okay, so 60 there. So that means this guy is parallel to this one. And this is the same as this one. So these two are the same magnitude. So this and this are the same, and with 60, so this will be a small equilateral triangle. Okay, so F1 for the magnitude, just the magnitude F1 should be equal to F21 should be equal to F31. Okay, so that's on that one. Similarly, for this one here, this is going to be F of 1 on 2. Okay, and then will be this guy will be also in that direction. F3 on 2. So these two add up should be something like this, goes in this direction. Okay, so there should be F2. It goes in that direction. For this one, it's going to be repulsive by 1, but attractive by 2. So in this way. So these two add up then in this direction. Okay. So this would be F of 2 on 3, F of 1 on 3, and this would be F of 3. Okay. So from the geometry, again, you'll see this is a small equilateral triangle. So this will be equal to this and that, which is also equal to this or this or this and this. So it looks like F1 and F3 are the same magnitude. Okay, so then from the geometry, you can tell actually F1 equal to F3, but less than F2 because F2 will be longer from the figure here. Okay. For B, it says now what's the directional angle of force by 1? So force by 1 here, this is 60 here, and 60 there. So 60, 60 here. So that means this is in the horizontal direction, which that means it's 0 degrees for the angle. Okay. For charge 2, so that's the 60 degree divided into 2 equal parts. So 30 degrees for each, right? And then directional angle, so this guy will be 120 degrees because it's 60 here, so 120. 120 plus 30, so that gives you 150 for directional angle. Directional angle should be the angle the vector makes with the horizontal. Okay, so 120 plus 30. On the last one here, this guy, so this is 60 equilateral triangle. So then that means 60 below the horizontal direction. Okay, so that's for this one. We'll take a look on a second example, and then that we will do today for today's lecture. So let's go back quickly. So this one says, it's asking you what's the force on the 5.0 micro, so mu for micro, Coulomb charges shown below. So this guy. Okay. So there are 3 more charges surrounding this one. So that means you want to just look at the 3 forces by those 3 charges on this one and then add them up. Okay. So let's quickly take a look on the sketch here. X and Y. So the positive charge is at the center here, positive charge, and on the origin. And then there's another one here, positive here, which is 3 meters away. So 3 meters away. This is 9.0 microcoulomb. This is 5.0 microcoulomb. And there's a negative charge somewhere here, which is also 3.0 meters away. And then there's a 6 microcoulomb, a positive charge there. So this is negative 3.0 coulomb, microcoulomb. And this is also 3.0 meters. Okay. So the forces will be on this one, right? Positive, right? This guy positive, positive will be going down. Okay. So that's that force. And then this one on this one should be going in that direction. Right, this one. So repulsive, positive, positive. This one is negative. So then we'll be having attract force on this one. So that guy. Okay. So you can say this one, this force, 2 and 3, those they will add up, okay? For the net force on this guy. So it looks like for the Y component, that will be just coming from this one. For the X component is coming from this charge and that charge. Okay. So we'll just look at the components separately. Okay. So for the X component, force of X is coming from the 2 forces. Okay. They are both in the negative directions. Now Coulomb's law says it will be K, Q1, Q2, right? So Q1, so let's look at this one first. So Q1, K times 9.0 10 to the minus 6 Coulomb, so microcoulomb. And the 5.0 times 10 to the minus 6 Coulomb, okay? Divided by the separation is 3.0 meters square, okay? And K is 8.99, so 8.99 times 10 to the 9, okay? Newtons, I think it's meter square over Coulomb square, okay? So that's the units on that, okay? So 8.99, and this is in the minus X direction, okay? Let's just take a note on that. Or for just for this one. And then for this guy, it's in the other direction. So plus, again, 8.99 times 10 to the minus 9 newtons meter square over Coulomb square for K times Q1, Q2. Okay, so this is negative. So 3.0 times 10 to the minus 6. Okay, so we are not doing negative because we'll have the sign indicating the direction. Okay, so then just magnitude for right now, which means absolute values times 10 to the minus 6 coulombs over 3.0 meters square. Okay, again, this is in the minus x direction. Okay, so those two add up. So you kind of calculate, and then it turns out everything add up to be, so F in the x direction turns out to be minus 30 times 10 to the third, okay, newtons. Okay, so that's in the x direction. So let's say this is the x direction force. The y direction force, F sub y, okay, so it's just by this guy. So it's in the negative direction. So again, K 8.99 10 to the minus 9 or 10 to the positive 9. Okay, so newtons meter square over Coulomb square, and then Q1, Q2. So Q1 6.0 10 to the minus 6 coulombs, Q2 5.0 times 10 to the minus 6 coulombs. Okay, divided by 3.0 meters square. And this is in the minus y direction. Okay, so if we talk about that direction, so this also turns out to be minus 30. Okay, times 10 to the minus 3 newtons in the y direction. Okay. All right. So it turns out that this guy should be minus of 60 in the x direction. Okay, because there's 9 on that one, and then pointing in that direction, there's a 3 on this guy, also pointing on that one. So these two should add up. So 9 plus 3 should be twice of 6. Okay, so this should be minus of 60. All right. So then the force, so you can write it as the force total should be equal to the x direction force plus the y direction force. Okay, so they could be just like minus 60 times 10 to the third newtons in the x direction plus minus 30 times 10 to the third, or minus 3 newtons in the y direction. Okay, so you can express in that way, or I can calculate what will be the magnitude and directional angle. Okay, so the magnitude will be you can calculate that. So the magnitude will be square root of fx squared plus fy squared, right? So square root of minus 60 times 10 to the minus 3 square plus minus 30 times 10 to the minus 3 square. So that gives you about 67.1 times 10 to the minus 3 newtons. So that's the magnitude. Directional angle theta equal to tangent inverse of f of y over f of x. Okay, so tangent inverse of minus 30 over x. That will give you the 26, about 26.6 degrees. But your x component is actually negative, so you want to add 180 degrees to it. Okay, so directional angle then turns out to be 206.6 degrees. Okay, on that. All right. So we'll stop there for today's lecture. Okay, so I'll see you guys next time. Bye.